So, hello everyone, and thank you for organizing this workshop, and thank you for inviting. As it was mentioned at the beginning, the workshop is also co-sponsored by European. It's a European network of AI-based robotics, and the idea is not to reinvent the wheel, but try to exchange methods as much as possible. I don't have slides on European, but of course these ideas of models and energy-based models is essentially if you want to interface things. Now, I wanted to talk about a little bit about this topic of the humanoids, and also discuss a perspective where I would like also to hear your opinion about that, because it's such a timely topic. We see those very impressive robots downstairs, and we have developed this for maybe 15-20 years with model-based approaches. Now it goes more and more on learning, reinforcement learning, and other approaches. But and I'm asking myself, what's still the role of models and model-based control, and how does this interact with the learning approaches, right? And I have the argument I would like to make is that I think that especially for the humanoids, which are also larger, not like the unitary, which can easily fall down and break, having a solid model-based ground on top of which you put learning, I think is the most stable or promising approach, right? But I wanted to discuss about also what's the technology, right? Because, we started with Ashimo like 20 years ago, and this was a purely position-controlled robot with a ZMP approach and so on. Then what we pushed forward is something based on force torque sensing in the feet and in the joints, and a passivity energy-based approach. Of course, we see the strong tendency towards quasi-direct drive, where you don't even need to model too much, because you hope that the reinforcement learning will take over and compensate for all the model disturbances. But on the other side, what we have done over a long time is a different approach, where we would like to control the energy and to store and recycle the energy. And I would like to give you some of the ideas in there and try to popularize this. This is also some work we have done with Cosimo. Cosimo is not here, but he knows my work well. So actually there were two trends, right? One is those rigid robots, and now quasi-direct, where you would like to have an actuation which transmits immediately to the rigid body model. And the other is, motivated from this very early work, which shows that exploiting the intrinsic passive dynamic has some sense, right? They have, this is a purely mechanical system driven by gravity, and then all this work which has shown that having springs and storing energy, is useful, right? And also those athletes, Paralympic athletes, they use the energy of the spring, and they can run and jump farther and faster than even normal athletes, just because they learn how to exploit this energy storage. So obviously, having compliance reduces impacts and so on, has some advantage. We have here, however, the talk of Marco Hutter, and said, those simplified models, they were always a strong limitation. And now you can use reinforcement learning, model the full dynamics, and learn on that incredible behaviors, right? So how to reconciliate? And actually, when robotics started, this is one of these famous videos of Mike Raybert, right? They had this concept of using compliance, using intrinsic energy, and having very simple controllers which just excite the energy in those systems. So what happens with the two directions? And is there a way to reconcile this direction of rigid robots, where we have just rigid body dynamics and try to learn, and then the approach where you use intrinsic dynamics? And I think having an approach which is models the energy flows and look at those and uses them for control is maybe a key to that. So the first part, I would like to say a little bit about how we are controlling our humanoids. So the specific thing is, probably you are more familiar to the cobots, right? The cobot technology, where you have a joint torque sensing and you have a very high quality torque interface, right? And you can use model-based control. You have compensation of friction, you have compensation of gravity if you want, and you have precise models of the robots, right? And this was key for the development of cobots, but if you see here, if you know the KUKA lightweight robots, our humanoid Toro just has the joints of 4 KUKA lightweight robots, and then it was built within maybe 1 year. And I think a key contribution here was a paper by Christian Ott and Maximo Roa and others at Humanoids 211, where he said, actually we could put together the whole methodology which has been developed for grasping and manipulation, and for locomotion. Basically in both cases you have parallel structures which interact with the body. In one case is the object to be manipulated, the other is just a fixed space. And it's about distributing forces in over constrained systems, right? And actually you could use the same approaches to do this planning. And you have the torque interface. So the basic, most simple controller which we have in order to control the center of mass is you define springs and dampers, so the classical impedance control for the center of mass, for forces and orientation. You have a desired range, right? Of course, you very well can describe the energy stored in that spring, the dissipation, and so on. So making a Lyapunov function and stability and convergence analysis is pretty straightforward. And then what you have to do is to distribute these forces on the various contacts. It can be the legs, but it can be also multi-contact with the arm, and so on. You can use optimization tools, basically, and model the unilateral constraints, the friction cone constraints. So basically, you have a force distribution problem as you have the force distribution problem when you manipulate objects with hands, right? You need to distribute the object force on the fingers. Here you have to distribute the center of mass force on the feet and the arms. And then from there, you just use the Jacobian transpose to go back to the joint. So it's the same framework we applied everywhere. And again, by monitoring the energy in the springs, the energy of the rigid body system, and constructing a storage function, you can prove dissipativity and stability and convergence and all these things which are not a little thing, right? Being able to prove that the robot, will always be stable and converge to a trajectory. I think it's essential for safety and certification aspects at the end. And the approach, I mean, here you see some examples. This is Ben Hence's PhD thesis. I mean, several best PhD George Gerard thesis awards came out of this framework. So what you see here is indeed this multi-contact, which I have told you, right? The center of mass is constrained to a desired position by a spring and a damper, and you can change contact. You are not bound like with a zero moment point only to the plane, but you can have contacts at every point. And because you have this passivity-based and energy-controlled approach, you can also, be in contact with uneven ground, even work on a mattress, because the big advantage of these energy-controlled approaches are that basically you are robust to interaction with environments which are also passive. So this mattress, of course, is a passive environment, so you can at least prove passivity and then stability and convergence. And you have all these hierarchical control approaches which have been pioneered, I don't know, by Osama Khatib and Bruno Siciliano and, the generation of roboticists in the 80s, but really working on the real system because you have this torque interface. And again, interacting with passive environments, right? You have a robot pushing a weight of 50 kilogram, things do not get unstable because you have, again, your control of you have full control of the energy in the system and the amount of energy which you inject. And still staying in a model-based framework, of course, what do you do with the center of mass? You can control it to a certain point, but you need to do also planning, right? And actually we came up with, I think, a very clear and straightforward way of implementing a planner for the center of mass. the point with the center of mass is that half of its dynamics is unstable. So it's a simple second order dynamics like over here, right? But you can split it into a stable and unstable part. Unstable part is just the pendulum falling down, right? And well, I cannot really go into the details, but the contribution of this framework is that instead of dealing with dynamics, so with differential equations, you know, computer sciences, the science people don't like so much differential equations, so they turned it into a geometrical problem. So you can define different points, right? This blue one is the center of mass, and this side, the red one, is a divergent component of motion. So this is the point which is unstable, and this V, this green point, is a virtual repelling point. So what happens is that you can describe the dynamics that in such a way that basically this red point is pushed away, so like with a magnet of the same pole, by this visual repelling point. Right? So this is the unstable part, while the center of mass follows stably, like, you know, attracted by two magnets of different polarity to this red point. So you don't need to care much about the center of mass, but you only need to care how you push your magnet away. Now, this is unstable and you don't like it, but the important observation is that taking a differential equation which is unstable and inverting the direction of time, it gets stable. So basically you can, you know, people say that if you walk on a mountain, you can close your eyes and then do 3 steps and then you will stop. Because human planning is kind of 3-4 steps ahead, right? So that's what we do here. When we do step planning, that's where I have, like here, right? You would do like a planning of 3 steps ahead. So from you know, the final destination, you could integrate backwards in time, and then your unstable part becomes stable. And the contribution of George Messerschmitt was to show that you can write this all together in a system of equations, the forward and the backward integration, and you can solve it analytically in microseconds. Right? So this kind of 3-4 step ahead planning, we have even closed analytic solutions for that, for the COM planning. Right? Again, don't have much time to go in the details, but I think the essential point is, you know, you have one unstable part, one stable part of the dynamics, invert the direction in time of the unstable part from your planning horizon, right, for your 4 or 5 steps. And you have to do the iteration forward backgrounds, and then you have 2 stable dynamics, basically, and you can compute, right? This is a RAL paper of George Messerschmitt, 2018, where he presented this framework. And then these are the solutions, again, purely model-based, and you can work on, you know, on the mattress, on uneven ground. It works very, very stably. You can even interact with the robot. That's another thing that, in contrast to inverse dynamics approaches, right, where interaction can cause problems because, you know, you don't have the effect of the interaction force. These passivity-based approaches are very robust with respect to interaction with passive environments. And okay, what about learning, right? I always tell my people, okay, in order that people believe you today that it makes sense, you need to put also the learning on top to see what's the contribution. And of course, if on top of these very passive approaches, you start learning whatever, iterative learning, reinforcement learning, to increase the speed, to increase the versatility, you still stay in this stable framework, right? You can prove on the lower level that you fulfill energy constraints, the context constraints, and so on, and you can increase performance by learning. In this case, we have a limitation of the speed of the joints, so this Popo technology, in contrast to direct drive, is limited in terms of speed, so Toro is not able to run. That's whatever you do, no matter if you use model-based or reinforcement or whatever, right? Unless you are a wizard, you won't make these robots run. But you can go at the limit. And the other point is stability, right? You still see those robots hanging on the cranes. So one big question is, how will we be able, under the current regulations in Europe, and I don't know what's the situation in China, but in Europe, if you would like to have a humanoid running in your home and you have kids, crawling on the ground, you need to prove at some point that the robot won't fall over your kids and kill them, right, or hurt them. And this is a difficult question to convince those agencies, right? And of course, I mean, there are all these different approaches to, model-based approaches to provide balancing. The question is, can you make it so simple that you can prove to a non-roboticist guy who does certification that you fulfill the bonds? And humans have all these different strategies. You have this ankle balancing, and then if the perturbation gets bigger, you start balancing from the hip, and then you go down in your knees. This also lowers your center of mass and makes you stable, and then you make step backs, right? You start moving your hands and so on. And Robert Schura, another PhD student of us, he extended our passivity-based approach to do this. And the nice thing about, if you want to speak about certification, is that he breaks it down to some simple geometric constraints. So, some of these points, if I go back, the blue point is the blue point, no, it's actually is the ECMP. So it's this virtual repelling point. You remember the magnet which pushes the unstable component. If you project it to the ground, there's another point, this ECMP. And basically, he reduced all the stability conditions to geometric conditions on the ECMP. So if you say, if the ECMP stays in this geometric area, the robot won't fall over, right? That's the simple statement. So instead of dealing with differential equations, you just have to say where some points have to stay, right? And the dynamics is hidden, encoded in the way those points are constructed. So that's the advantage of this formalism. Okay, so just to understand what's going on. And in this case, for the robot balancing on a rectangle, the condition is relatively simple. The point has to stay in this area, which is bounded by the feet. And when the robot approaches the end of this area, it switches between different phases, right? So, as I told you, you have the ankle strategy. At the beginning, it starts just balancing the ankle. If you come to the ground, towards the limit of this region, then the robot starts with the ankle and with the arms. And then, well, in this case, it won't do any steps, but it's doing all these compensations. And in the next video, you will see, it even works on one foot, right? And this video shows also the switching between the different phases. So different posture recovery phases. And even for that, you can show, of course, as long you are not going into limitation of torque or velocity, and as long as you stay in this area, your robot will be robust. And you see, although we have these recovery strategies, right, based on simple concepts, complex whole body motion emerges out of very simple principles, right, of maintaining stability, of using your degrees of freedom to keep your energy bounded and to keep your balance. So this looks very natural, although there's no planning, actually, there's just the control-based reaction. And yes, here's some more videos. What's going on? So you see, you put it for the side, the robot rotates, and this comes from the very basic first principle motivated approach. And passivity-based control also means you can interact with the robot, right? I also told Robert, I mean, he's pushing with the stick at the beginning, of course, because he's cautious, right? The new method, you should be cautious. But I told him, you should actually show that you can go and touch the robot, right? It's not that the robot is going to go crazy, right? You can go there, touch it, and you have seen also the step recovery at some point. So, and I think on top of that, of course, the way you plan and the way you do strategies and react to complex environments, this should be learned on top and have reinforcement learning. But I think then you don't need to care about the stability of reinforcement learning as long as you show that your geometric constraints are fulfilled. As long as you learn within these boundaries, you cannot fall over. So, you know, the learner can do better or worse results, but at least you make sure it won't tip over, right? So you explore in a space of feasible solutions instead of exploring in a space of everything, right? Still, we need to prove that it's more efficient, and this is work which is going on, and I hope that we soon can provide results. And as I told you, Toro cannot run, right? So we can simulate how it could run and show that the framework could do it in principle, and we hope to build a robot now which can run, and we have one of the robots you can see downstairs. We have the P&D Adam robot, and we transfer the approach on that robot, and I hope that we can show that the same framework, planning framework, can be used for running. Okay, this is my part one. Okay, I spent too much on it. Let's go to part two, exploiting intrinsic dynamics, where you would like actually to go even deeper and while running, right, not dissipate energy every time you touch the ground, but store energy and have a continuous control of the potential energy stored in the elasticity, kinetic energy, actuator energy, dissipated energy, and so on. That's the idea, and because, you know, if you look at this kind of running, this is still different from whatever we say downstairs in the exhibition and we have seen before, right? And biological bodies are compliant, and nature seems to explore it. Now the question is it just a bug because nature could not come up with rigid actuation, or is it a feature, right? Is the elasticity in our muscles and tendons something which makes biology more robust, right? And this is the topic I explored. I always show as a motivation this beautiful work of David Remy, who has shown that in simulation that even, you know, a passive system, if you give it the right initial condition, you generate all possible gates of quadrupeds. Again, no actuation, just passive dynamics, springs, inertias, and initial conditions. The point is, such a system is, if it's conservative, it's chaotic, right? So you have a complex, several, you know, if you look at each leg as a pendulum, they are chaotic systems. So we see this nice oscillatory behavior like here, right? How does biology succeed to make these periodic oscillation motions out of a system which is potentially chaotic, right? This is the question which we posed ourselves. We use differential geometry to model that in the first instance. I had also an E-RLC grant which ended last year. And of course, you want to model the elasticities of tendons and muscles, right, with springs and dampers and rigid bodies, and then look for periodic trajectories of this. So this was my main topic of the E-RLC grant, and so how do you describe periodic motions of such systems, right? I mean, this is the analogy, of course. I think it's pretty clear for people used to think about energy and models of systems. And this is some robot we built. It's not a great quadruped. It's not competing with a unitary quadruped, but it's used, you know, using 3D printing and RC servos. But the idea is to have in the joints elasticities. We build in some springs and to research how you can use these elasticities. And you see here, the motors are fixed. So this is the mechanical compliance of the system. It's very compliant, similarly compliant to how biological muscles are, right? And okay, so you want to make the system run in resonance. We all know linear theory of linear model theory, right? It's what every engineer learns. But linear theory is not useful for running, but because running is high amplitude, right? So you're not in the linearization small oscillation regime, but you want to oscillate at your maximum possible amplitude. So linear oscillations, we all know, right? You do eigenvalues and eigenvectors, and then if you excite along an eigenvector, then you will always stay on that eigenvector. Second order system, right? You have two eigenvectors. You give it an initial condition, you will stay on that line, right? And if you plot it in configuration space, these are just straight lines, and you will oscillate on those straight lines. If you plot it in position and velocity, then there will be ellipses, right, in that space. I mean, this is just where we start from, right? And yeah, I mean, if you have two masses, this is from a paper I wrote with Cosimo together, right? Then one mode is in-phase oscillation, where both masses oscillate in phase. The other mode is anti-phase oscillation, where the masses go one against each other, right? And you see here in state space the two lines. What does it happen if you have a double pendulum and you have nonlinear couplings between inertias and so on? Do you have something like modes as well? The answer is yes. The only difference is that instead of oscillating on a line, you oscillate on a curve, right? And you will, it's still an unproven conjecture since 80 years of mathematics. There are long proofs which on arXiv, which have been not yet published, that indeed for any n degrees of freedom system which has n modes, you know, linearized modes, you will have also n nonlinear modes. Without having a proof, we have the MATLAB toolbox to find them. You give me the system and the equilibrium point, I will give you the n modes, right? So practically it's there, the conjecture is not mathematically fully proved. You will find a lot of papers claiming that they prove, but obviously it's not completely decided. Now, how do those modes like? If you increase energy, right, for a linear mode, you know, you are staying on the line. For the nonlinear mode, those curves start to bend because you move on some manifolds. Without going in details, if you saw it in 3D, one of the modes is pretty linear. You see it starts bending at the ends. But the other one is it's really nonlinear, right? And it's oscillating quite strongly. And the more you increase the energy, the more nonlinear it gets. But you know, if you cut it with a horizontal plane, it will be one oscillation at one energy. And you see that, you know, you can go higher and higher energy and still stay on those modes. So the idea is to find them and exploit these oscillation modes. They are all for conservative systems. That's a limitation. So you have to go from the conservative modes, just compensate energy, and the hypothesis is that you have a system which has so little friction that this description of the nonlinear oscillations is good enough. And this is for, let's say, a leg or an arm. These are the two modes, right? One is, you can see what they do, right? And actually, we use them, right, for throwing balls or for running. One mode is just like this, and the other one is like this, not surprisingly. And you can use them up to swing up a double pendulum to this position. You can always go along that mode. So I think they are pretty useful things if you want to be energy efficient, right? Stay along these natural modes, right? And then we took the model of our quadruped robot. First of all, fix the legs to the ground, so put, you know, ball joints to the ground. Then you have just 6 remaining degrees of freedom. And these are the 6 modes the system has, right? So you start from the linearized modes, from the small amplitude oscillation, and then you increase the amplitude, and look what the robot is doing. And it's doing this kind of things. Looks like what? Maybe you have some ideas which kind of motions the quadruped would have. And well, the control idea is then, if you have those modes, you just need to inject the dissipated energy. So, you know, instead of going in 1 millisecond and controlling the position every millisecond, you just give it the energy and let it swing at this natural frequency. If the natural frequency does something meaningful for you, which means you are also doing a co-design, right? Because if you build a robot which runs, you should analyze its modes in simulation, and then maybe change the mechanical design, change the controller, until the robot more or less runs by itself, and you then just have to kick it at the right time, right, and in the right direction. Okay, now this is a validation that those modes, if you do in simulation, you can find them. If you put friction, then they stay still close, but they have some hysteresis. And then if you do it on the real system, they still stay close, and you can just excite them by kicking the robot a little bit at the endpoints, right? And then, this is a paper which is still in the review process. You know, you're just exciting by kicking them, and it's doing these things. And if you release the feet and just give it also some forward velocity, they start to develop into gates, right? It's not a perfect gate, but they all develop into gates, right? They start moving in this oscillation pattern. And then we had some experiments on the real robots, and you do exactly the same thing, and the robot starts walking. And the two modes, they did not work because our actuators, this RC cell was just too weak. And the belt started to slip, so that's why we could not implement these two, but all the others, right, we just excite modes, the robot starts to walk, as you see, in different patterns. So one mode goes into gate, the other goes into bounding. Well, this is a pretty, we call it the sewing machine mode. I don't know if it's really useful, but it's maybe due to the fact that our mechanical design is not ideal, right? this is what our robot can do. They have equal springs in all joints. You can do better on the design, but it's just exploiting the oscillations of the system. And these are some further examples where you use just this intrinsic simple oscillation to generate gates. Well, how much? Okay, time is over. Then I won't go in the details of the geometry. Just one main statement. What's the mathematics behind and why do mathematicians have so big difficulties? Basically, there's a concept of geodesic curves, or shortest paths of manifolds, and you can link this concept over an energy concept, right, to geodesics. So intrinsic motions of robots are geodesics along special manifolds, right? I won't go into the details, sorry, it's too long, but actually finding periodic motions is finding geodesic curves on some manifolds, right? And this is a very classical topic in mathematics, and you can exploit a lot of things. I don't know, how many of you know the book of Arnold on differential geometry? I was intrigued by a statement, you know, this is a picture from the book of Arnold saying, for every double pendulum, you will find a periodic trajectory doing n turns around one joint and n turns around another one, right? And there's a simple proof. Basically, it's just because you can wrap a string n times around the torus in one direction and the other, let it contract, and it will be a geodesic, so it will be a trajectory of the system. It's that simple. So it's a relation between geodesics and trajectories. And using this tool, you can find not only these modes, but a lot of other modes, right? So Arne has a toolbox, one of my PhD students, and then you just take strings, let them contract on the torus, and you will find periodic trajectories. Like for the double pendulum, not only those spinning back and forth, but you know, all these motions you can do at, in principle, at zero energy, if you except for compensating for gravity. Right? And there's plenty of them. You remember we discussed about the system being chaotic. Yes, it is chaotic, but chaotic systems have a lot of periodic solutions as well. You just need how to know how to find them. And now we are building, you know, a direct drive double pendulum to really recover this. Also, Manuel is involved in this work. I want to, you know, simulation is nice. I want to see them in real, that you can do these kind of things forever with a small battery at almost, you know, no energy cost other than compensate. And it's plenty of them, right? It's plenty of them. You remember, I don't know if you've seen the Rain Man movie, right? When he's counting cards and he's saying, don't worry, there's plenty of I don't know what he was looking for, acids. There are plenty of periodic trajectories in a non-linear system. You just need to know how to find them. You know, interestingly enough, free body problem is the same question, right? Free body problem is chaotic system, but you will find on the internet, on YouTube, a lot of images where using similar tools you can show that free body problems do periodic, so there could be stars doing this kind of free body ballet periodically. Okay, and the last is Davide Calzolaris. He used this concept of you know, periodic orbits which increase with energy, and has a controller which basically, you know, on one side you inject energy, on the other side for each energy you stabilize on your periodic orbit which you found. And he could show that, you know, you can stabilize that again with very simple controllers, stay on this tornado, how we call it, of periodic orbits, and inject energy to increase energy the way you like. And this is his controller, again, exciting the intrinsic mode. And then the learning on top of it, of course, you can do learning. And I want to show just the final video. These are three approaches on the prototypes we have. One is with the linear modes, one is with these circular modes, and the other one is with reinforcement learning. I won't tell you which is which. The reinforcement learning is the slowest in that case, but I'm not sure that you could not do better, right? But what I'm happy is that we have three PhD theses exploring three approaches: learning, linear mode, non-linear modes, you know, end-to-end, so these break orbits and these tornado orbits, and they all kind of work effectively on the system. Are we there? No, we are still far away. You know, this is motion tracking for a dog. But I still think that considering energy and energy storing methods is a better way of describing that than just learning, you know, purely motion tracking and transferring it on the system. thank you. We are still far away, but maybe you can get some.
Yeah, thank you very much. Yeah, thank you for your very interesting question. Unfortunately, I have the duty of stopping all this in the talk. They could have been lasted for 1 hour, in my opinion, but we have a schedule. So we can have one question. Yeah.
Hi, very interesting talk. I was just a simple curiosity. The manifold of the quadruped is isomorphic to which possible manifold? Just to have an idea of the dimension. And
So the topology is first of all that of a torus, n-dimensional torus, because we have rotationary joints. But if you look at the metric, then the metric is determined by inertia, right? I mean, if you look at relativity theory, they do the same interpretation. They say that inertias deform space, right? I mean, this is the key is also if you don't go at relativistic speeds, you can describe motion as geodesics on some tori which are deformed by inertia. So where you have big inertia, the distances are bigger. Where you have small inertia, the system. So think about the torus, which is, has some inflated areas where the inertia is big and shrinks where the inertia is more or less. Then you have to include also potential energy. So there's a special metric called the Jacobi metric, which deforms the torus according to this metric.
Thank you.